Okay, so welcome back. So in the previous class we were discussing about the case study of die filling in case of semi-solid die casting. So we will go ahead with that section of the course. Like we have discussed the appropriate rheology models and also the solid fraction versus temperature curve in case of aluminum 7 silicon 0.3 magnesium alloy. So as we have also shown that we have investigated the viscous evolution at 3 different temperatures 605, 580 and 590 purposefully, because these temperatures are relevant for optimization of die filling attributes of the component cavity, and we have also performed the die filling studies for these temperatures. So the importance of slurry injection temperature. So it controls the filling of the component cavity and subsequent solidification of the component. So the temperature distribution impacts the flow and solid fraction within the die. So the observations from experiments are so pouring temperature 585 and 600 degrees centigrade. So the unfilled regions were evident. So if you are that will be shown in the next slide. So we will come back to that. So this is basically the contours of solid fraction evolution in case of, so this is basically a automotive knuckle housing, CKLE. So it is basically a part of the steering component of the automotive engine. So this is, you can see a case of filling with 585 degrees centigrade pouring temperature, where you can see a large unfilled region which is the integral part of the component over here, and also you can see the overflows are not filled, so like here. Which that means overflows, what is the function of overflows here? The overflows are basically responsible for providing the extra space, and also they are responsible for trapping the darts, inclusions which are present within the melt, and also some gas porosity, so that within the actual component geometry it becomes free from defects. So that means if the overflows are not filled at that temperature, so the solid fraction is not there, means they are not filled, so the defects chances of defect formation within the component is very high. So that's why we need to discard that. And even when we are increasing the melt pouring temperature to 600 degrees centigrade, we can still see there is a significant portion of the component is unfilled, although it is improved than the 585 degrees centigrade, but you can see the overflows are still not completely filled. So we cannot go for this, choosing 600 degree centigrade as the pouring temperature of the slurry, semi-solid slurry, which is having a significant solid content. Solid content based on the temperature we can determine based on the solid fraction versus temperature curve for this particular A356 alloy that we have discussed earlier. And then if we move ahead and increase the temperature further, in case of 605 degrees centigrade, you can see that of course the flow behavior is much better within the component cavity. We can see the overflows are successfully filled. However, you can see the overflow at the top of the top leg of the knuckle housing, and also at the top of the tensile specimen bar is not filled yet. So then further increase of the melt temperature to 610 degrees centigrade, which is having a minimum solid content of if we go back to the solid fraction per stage temperature curve, so then we can see that here the solid content is somewhat around 0.1. So in that solid content, which is enough for promoting spheroidal microstructure within the solidifying knuckle housing, and thereby achieving improved mechanical properties, and to achieve the advantage of semi-solid Rio die casting it is enough. So in that case you can see all these overflows and all the parts of the component cavity has been filled successfully, as evident from the solid fraction distribution, which is rather homogeneous, and throughout the component for most of the sections you can see it is lying, based on the color code you can see that it is lying between 0.1 to 0.3. So that means there is a 20% more solid which is generated during filling, because these are all during die filling stage. So here from also you can understand that during filling there is a significant temperature drop happens within the flowing and solidifying melt, and also it is responsible for solid generation during filling. So that's why we need to account for the viscous evolution of the solidifying melt while considering the die design attributes and to optimize the process conditions. So if we go back to the solid fraction findings that we have discussed over here. So so the pouring temperature in case of 585 and 600 that we have already discussed based on the contour of solid fraction distribution. So other than the unfilled regions, it also indicates poor filling capability of the melt at those two temperatures because of the higher solid content present within the melt, and also it poses higher risk of oxide skin entrapment and gas absorption within the component cavity, which is strongly not desirable because it can result in scrapping the component. So we need to avoid that. And at 605 degree centigrade, only overflows were found to be unfilled, although better than 585 and 600, but still it had issues, and all those issues are met in case of 610 degree centigrade. So found suitable for die filling capability and casting of this Al7 silicon 0.3 magnesium alloy, which is having a commercial name as A356. And so in this case of that means at 610 degree pouring temperature, we could achieve uniform solid content distribution ranging between 0.1 to 0.3% solid, 0.3 volume fraction Fs within the throughout the component, except the overflows, which is not significant anyway, though they are basically going to be part of the parts to be removed during the fettling stages. And then minimal variation in slurry temperature within the cavity, that is point number 3, which is met, and which is also evident from uniform solid content distribution within the component cavity after solidification, and then preferred pouring temperature for the studied condition. So accordingly 610 degree centigrade has been identified as the ideal pouring temperature for semi solid die casting, Rio die casting of the melt. Okay. And then coming into the further details of the solid fraction. So here we have discussed about the importance of melt pouring temperature. Now we will discuss about the temperature dependent issues. So lower temperature shows non-uniform solid fraction distribution, as we have seen in the contour that we have discussed just after this. And then lower temperature shows non-uniform solid distribution and causes greater variation in slurry temperature, and higher temperatures causes optimal pouring temperature should be sufficiently above the eutectic temperature of the alloy. That is what I have discussed with you earlier also, because below eutectic temperature, if we choose a particular melt pouring temperature and it results in generation of the drop of the melt temperature during die filling stage below the eutectic temperature of the particular alloy, in this case 577 degree, then the solid network which gets built within the solidifying mush, solidifying melt, it becomes so thick, and it becomes the flow becomes impossible, and that is why it is prone to generate defects within the solidified parts. So it is preferred to be above eutectic temperature always within the filling stage of the component. So accordingly the pouring temperature should be chosen, and also higher pouring temperature, relatively higher, not with of course it is still below the liquidous temperature of that particular alloy, because to take advantage of the semi solid die casting, or more appropriately the Rio die casting, RDC. So it ensures better homogeneity and reduced defects, and the recommendations are for RPDC, which is also can be termed as RDC. Slurry temperature should be below the liquidus and to have temperature and above the eutectic temperature to avoid defects like shrinkage cavities and hot cracking. And proper temperature control results in uniform solid fraction distribution, minimum casting defects, and improved compositional attributes, compositional so reduce segregation and improve microstructural homogeneity. So further details of this case study can be found from our earlier work published in Journal of Materials Processing Technology. Okay, so this contours of solid fraction distribution within the solidified knuckle housing, I have discussed this to you earlier. So we will move on and we will show the temperature distribution contours for the 3-legged. So this is basically leg 1, L1, and this is your L2, leg 2, and this is your leg 3. So this is a steering component. So knuckle housing. So you can see that effect of temperature distribution of the solidifying slurry during die filling stage is quite similar. Observations are quite similar what we have observed in case of solid fraction, because temperature and solid fraction are like complementing each other because they are closely dependent on each other. So similar findings we have observed that in case of 585 and in case of 600 degree centigrade, there are significant unfilled regions within the component. So you can see there are unfilled regions of leg 1 for in case of 585 and 600. So they are easily discarded to be chosen as a pouring temperature for further Rio die casting and component development. And in case of 605 degree centigrade, although all these legs L1, L2 and L3 are filled satisfactorily. However, it is evident that there is overflows are not filled, and I have already discussed to you that if the overflows are not filled, that means there is a chance of defect formation within the component cavity, within the component body, and so avoid all such occurrences, we have chosen 610 degree centigrade as the ideal pouring temperature, where you can see that we can basically successfully achieve the filling of the entire cavity of the component, and also we could successfully fill the overflows as well. So all these overflows are filled, that means the chances of defect formation is also minimized within the component body. And also you can see that temperature distribution is more or less uniform, which is lying between 600 to 610 degree centigrade. That means the temperature distribution is more or less uniform, which also complemented by the solid fraction distribution just shown before this slide. Here also we have seen that solid fraction distribution is more or less uniform. So that's why it has been identified as the optimum melt pouring temperature during Rio die casting processing of the solidifying melt. And so the cases of entrained air. So the findings on entrained air, it is we have discussed in the former classes of this section, that it is very important that gas absorption, air entrapment in case of die filling, because they are responsible for pore bubble formation within the solidifying component, and that in turn causes makes the structural integrity of the components weaker, and it also serves as the potential sites from where the cracks nucleate and leads to the catastrophic in-service failure of these components. So, so that's why it is very important to study these attributes. So, entrained air, number 1 is volume fraction of entrained air. So, the so this is the contour which is shown, where you can see that similar like the pouring temperature, temperature and solid fraction distribution, we can see that in case of 585 degree centigrade, there are significant unfilled regions where volume fraction of entrained air is between 0.3 to 0.4, and also there are unfilled regions as well in case of 5. So you can see that this is in case of 600 degree centigrade. So so in case of, so this is basically 585 degree centigrade and this is 600 degree centigrade. So from here one thing is very clear, as we have seen in the in the earlier contours, like in case of solid fraction and in case of temperature distribution, this defect at the leg 3 of the component of that means knuckle housing was not very clear, which is clearly evident from this contour. This is the unfilled region prone to defect, so which discards 600 degree centigrade as well. And then in case of 605 and 610 degree centigrade, the differences in case of entrained air distribution is quite similar to that we observed in case of solid fraction as well as temperature distribution. And so entrained air volume fraction distribution also qualifies 610 degree centigrade as the ideal pouring temperature for Rio die casting filling of the A356 melt to develop this 3-legged knuckle housing. Okay. So the entrained air here as I to summarize the findings. So higher entrained air fractions observed for pouring temperatures 585 and 600 degree centigrade, particularly in the central hub of the 3-legged knuckle housing, and volume fractions where ranges between 0.2 to 0.3 with localized regions reaching 0.3 to 0.4. And the modeling of air entrainment. So how we have basically modeled air entrainment in the die filling simulation that we have depicted here. So here air entrainment happens at the free surface of the melt. Here in this case for Rio die casting it is the semi solid slurry, and here it is modeled in flow 3D platform using a diffused quantity approach, and a passive scalar variable is used to track air volume fraction without altering the flow dynamics. And here also the air bubble model is implemented for bubbles trapped in moving fluid. So as per as the adiabatic bubble model as per Hurt. So this is how we basically track the air entrainment at the free surface and also air movement of the bubbles porosity which are trapped within the solidifying melt. Earlier in this section we have already discussed about the porosity formation model. So I hope now you can understand how this is useful to model the actual entrained air and also bubble formation during actual die filling studies of a component by which we can optimize both the design attributes of the components and component cavity and also the process attributes to achieve the desired component with the desired quality characteristics, the microstructure and mechanical properties. Okay. So the viscosity profiles, so rheology model effectiveness. So this is the viscosity profile shown over here. So we will come back to this. So basically so it shows the rheology model that is developed in this case study, like what we have discussed before, and further details can be found in this publication. So confirms the effectiveness of the developed rheology model used for die filling studies for Rio die casting, and the viscosity profiles highlights the impact of shear rate and temperature variation within the die cavity. So you can see that as where temperature is higher, there solid fraction is lower and viscosity is lower, and simultaneously there is a complex interplay between the temperature and shear rate. Although there are occasions where there is same temperature, however shear rate is higher, so that is why the viscosity is lower. So these viscosity profiles that is shown after 2 slides. So it shows the viscosity evolution for different slurry pouring temperatures. That means for 585, 600, 605 and 610 degree centigrades. So these are the observations. So at lower temperatures, so that means in case of 585 and 600 degree centigrade, higher slurry viscosity is observed within the die cavity, component cavity. That means in case of A and in case of B, you can see, as we have seen earlier only, that there are several unfilled regions, and the viscosity evolution is also quite high in these regions. So you can see that localized viscosity evolution is observed in this case the leg 3, which is basically gives the reasoning behind defect formation. So higher viscosity, this red color here shows the viscosity is beyond 0.5 or near to 0.5 Pascal second, and that is the reason that it impedes further flow of the, doesn't allow the melt to flow effectively and fill this region, and that is why this region we have observed defect formation earlier also when we have compared the temperature and solid fraction distribution contours for this dye filling study. Whereas you can see that although the viscosity is relatively high in this region, that means in case of leg 3, in case of 605 degrees centigrade, however, it is completely filled and there are no defect. Why? Because in this case the shear rate is enough to check the viscosity in the tolerable limit, and the temperature and the solid fraction is more uniform. So, however, because this section shows that there is chances of defect formation in leg 3 in case of 605 degree centigrade as well, and hence it supports the earlier conclusion of not choosing 605 degree centigrade as the ideal pouring temperature, whereas no such difficulty is observed in case of 610 degree centigrade pouring temperature, which is also considered as the ideal pouring temperature for Rio die casting processing of this A356 alloy, and where you can see that even if there is chances of defect formation, that is there in the tensile sample, and the component, you can see that leg 1 and leg 2, leg 2 and leg 3 of the knuckle housing, there are viscosity distribution is more or less uniform, and viscosity distribution is also relatively lesser. So, apart from some pockets, the viscosity is within 0.2 Pascal second, and that that signifies that improved flow behavior of the solidifying melt within the component cavity, and also uniform points towards uniform temperature and solid fraction distribution that we have seen in the earlier slides, and that is why this has been considered as the ideal pouring temperature from viscosity distribution findings as well. Okay. So, so that means 610 degree centigrade shows almost uniform slurry viscosity suitable for effective filling of the die cavity and exhibits better flowability and reduced defect generation. Okay. So, now so since we have discussed two case studies on this gravity assisted low superheat casting, while we have optimized the cavity and the process conditions to develop as per ASTM standard tensile specimens, and also in case of Rio pressure die casting, where we have discussed the die filling studies while developing a 3-legged knuckle housing. So, here now we will just show the steps for your ease of understanding the how to basically execute the die filling. So, this is an example shown to you to apply the theoretical knowledge to perform the real life die filling studies. So, number 1 is defining material properties, number 2 is adding geometry of the die cavity and mold, then the disintegrating discretizing the computational domain for mesh generation, then applying boundary and initial conditions and providing metal input, and then initialize the model giving initial conditions and heat transfer studies, and then finally the result generation. So, these are basically the platform, several input parameters, that is solidus, liquidus, temperature, critical fraction solid, latent heat of fusion that need to be provided for simulating the die filling behavior of a particular alloy melt, and these are basically shown in case of aluminum alloy, that is A319. So, where you can see these are the reference temperature, and temperature dependent specific heat and thermal conductivity is provided, and thereby you can. So, this is an animation of a ring shaped component where you can see how this die filling is useful to optimize the sprue dimension and also the this is the runner dimension and also the in-gate dimension. So, this is the in-gate and also the process conditions. Okay. So, you can see the free surface defect in generation within the component, which is fairly lesser. So, so this is how basically the the input condition. So, this is the sprue inlet. So, this is basically serving as the pouring basin, and this is the top open riser. So, and then this is the computational domain mesh that is utilized for studying the die filling behavior, and this is the casting cavity, walls, wall temperature, and die material has been considered here as the hardened steel. Okay. And so these are some further results. So, this was the case of filling that has been shown over here, and this is the case of solidification that is over here. So, it is the solid fraction evolution. You can see that basically it is getting solidified and solid fraction. So, you can understand that it is the riser which is solidifying at the end, which is also desired, and you can see because of the height decrease from that it is capable of feeding the solidification shrinkage as well. And so, this is these are shown for this mining excavator links that has been developed within the scope of our research, our group's research. So, those are you can check our group web page to get further details on that. And so, now we have discussed in detail about the die filling studies. So, so this is basically this is the final slide of this section of the die filling section of the course, and where we can see that the effect of grain morphology over cooling rate. So, you can see this is a case of conventional solidification under gravity that we have discussed earlier. So, there is a wall chill zone or equiax zone, then there is a columnar zone, and then there is a equiax solidification at the middle. So, this happens because of the temperature gradient ahead in the solid liquid interface. So, we have discussed about this in detail while we have discussed about the solidification micro mechanisms at the beginning of the casting solidification module. So, here the grain morphology of phases depends upon impurities and thermal gradient, and the grain growth in the opposite direction of the thermal gradient. So, that is quite clear. So, because heat is getting removed from this direction from wall, and the perpendicular to that it is the growth direction of the solidifying columnar dendrites. So, thermal gradient and dendritic growth rate decides if the grains are dendritic or equiaxed in shape. Okay. So, this is how the mold filling has been done, and after filling and even during filling, when it is filled up to some level, the solidification starts from the wall. So, you can see this table basically summarizes. So, you can see that so this is the dendrite growth rate R, and this is the temperature gradient capital G. So, you can see that for a increasing dendrite growth rate, when dendrite growth rate is limited to a certain value, then with the increasing thermal gradient the shape is goes to columnar and then cellular, and then it goes to the planar front. Okay. As the dendritic growth rate increases and simultaneously the temperature gradient also increases. So, in case of lower cooling rate, we can see this kind of microstructure, that means coarser cellular structure and coarser columnar and equiax dendritic structure. However, with higher cooling rate we can see much finer columnar primary solid, and that is the case in case of dendritic column that is the case in case of columnar dendritic and equiax dendritic structure as well. So, G cross R, that means the product of temperature gradient and dendrite growth rate, determines the size of the grain, whereas G by R, that means temperature gradient divided by the dendrite growth rate, determines the morphology of the grain. So, this is how the size and morphology of the grain are determined. Okay. So, with this we are done with this module of die filling analysis of the solidifying melts, while we are optimizing the cavity design and process conditions for the for a given material or given melt, as well as the given given melt and also a given component cavity. So, so we will meet with the next section of this module soon. So, till then, thank you very much.